Today we're going to look at how to extend our natural deduction system from propositional logic to predicate logic. What does that mean? Well, we keep everything we had in propositional logic, but now we add a couple of new rules to our system. And in particular, we add rules governing the use of the quantifier. Remember, the idea behind predicate logic is that it adds additional structure to the language. Whereas our basic units of analysis in propositional logic was the proposition, now our basic units of analysis are objects and predicates. So for example, R here is a predicate. In this case, it's a relational predicate, and it takes two objects as its arguments. Since the propositions can be as complex as you want, you can string together a number of different propositions using the logical connectives. We use these phi x notation to stand in for any arbitrarily complex formula. So it's important to be able to understand how the arbitrarily complex formula relates to its more specific denotation. That is, a substitution is when you take the argument of a propositional function and input a different argument by systematically substituting in the new argument for the old argument. A substitution is when we take a formula that contains variables and systematically substitute in an individual constant for that variable, or the other way around. So let's look at some examples. Here we have, if phi x is the formula rxb, then phi a is the formula rab. So what's the difference between rxb and rab? Well, wherever there was an x in the original, now there's an a. So phi x is the original, and if that's the original, then phi a is the result of going in, and anywhere we see x, we put a in instead. Remember, x here is a variable, a is an individual constant, denoting some particular object like Anne or Anne's pet fish or whatever it may be. And if there had been more occurrences of x in the formula, then we would have had more substitution instances for a. We would have put in a wherever there was an x, even if there had been 3, 5, 6, or 1,000,000. We can go the other way around as well and do a substitution where we start with a formula that has an individual constant and put in a variable anywhere we see the individual constant. So if psi a is a formula fa and ga, then psi x is the formula where all of the a's have been replaced by x's. We can also do substitutions incorporating the quantifiers. So notice that in this example, the quantifiers there were no quantifiers. The variables here are free. In this case, we're going to do a bound variable substitution. If phi a is the formula rab, then there is x such that phi x is the formula there is x rxb. So all we've done here is we've gone through and again replaced the individual constant with an x, and then we've bound that variable with a quantifier. Part of the challenge of doing proofs with quantifiers in predicate logic is that you have to be able to stare at two formulas and recognize that they are of the form phi a or there is x phi x. So again, these are the forms of these more specific propositions, and it's important to be able to recognize the form of a proposition. So consider these two. Now pause the video for just a moment and try to figure out the following question. Try to find phi x such that 1 is phi a and 2 is there is x phi x. So now that you've unpaused the video, compare your answer to the correct answer, which is this. For all y, r, y, x. It's easy to verify that this is the correct answer. Why is that? We were trying to find a formula such that number 1 is that very same formula, except with all of the instances of x substituted with a. So here we have exactly that. The same formula as number 1, except all of the instances of x had been substituted with a. And number 2 is the same formula, except that X is no longer free as it is here, but rather is bound by the existential quantifier. And that's exactly what we were looking for here. So substitution is important to have a grasp on because you need to have a good grip of what the forms of these propositions are.